lulusan yang unggul di tingkat nasional maupun internasional dan berkontribusi pada pengembangan ilmu pengetahuan, teknologi, seni, budaya, serta olahraga.
Sudah saya siapkan Pak semuanya Pak.
Langkah besar yang akan dilakukan Undip
sudah ada, ini sudah disiapkan
masuk dalam 500 World Unity Rank. Kami akan terus memperbaiki aspek-aspek pendukung, mulai dari regulasi internal kami, peningkatan sarana dan prasarana, sistem keuangan, tata kelola birokrasi, sistem informasi, serta meningkatkan kualitas sumber daya manusia, peningkatan kualitas Tridharma perguruan tinggi. Menjadi target utama Universitas Diponegoro dengan terus mendorong hilirisasi hasil riset agar berguna bagi masyarakat. Diikuti dengan peningkatan publikasi nasional dan internasional, serta meningkatkan jumlah doktor dan profesor di lingkungan Universitas Diponegoro.
Undip telah mendapatkan predikat World Class University di Indonesia dengan menempati posisi ke-8 dari 4.625. Sementara prestasi mahasiswa dalam event bergengsi di tingkat nasional maupun internasional terus mengalami peningkatan. Visi menjadi universitas riset unggul didukung dengan dana riset yang terus meningkat. Total dana penelitian dan pengabdian masyarakat di tahun 2018 sebesar 123,7 miliar yang terdiri dari PNBP, dana riset kompetisi nasional, dan dana riset kerjasama. Hak kekayaan intelektual atau HAKI yang menjadi indikator kinerja penelitian mengalami peningkatan drastis. Paten yang dimaksud meliputi paten sederhana, paten internasional, software, dan surat pencatatan ciptaan. Untuk mendukung proses belajar mengajar, Undip terus membenahi layanan fasilitas mahasiswa sehingga di Undip, mahasiswa tidak hanya mendapatkan ilmu pengetahuan, namun juga memiliki ruang untuk aktualisasi diri.
Mas Faisal, suaranya dikecilin. Mas Faisal, suaranya dimatikan dulu.
Iya Mas Faisal, benar nih.
Halo, Yamaji Sensei.
Oh, hello. Do you hear me?
How are you, Yamaji Sensei?
Nice to meet you.
Genki desu ka?
Yes, finally we meet.
Oh, yes. Nice to meet you, Sensei.
Nice to meet you. Thank you for your invitation.
Yeah, you're welcome.
Ohayo gozaimasu, Aki Fumi Yamachi Sensei.
Hello.
Hello, welcome to our university.
Thank you. Thank you for your invitation.
Watashi wa Eko Kyoto Daigaku no alumni desu.
Oh, really?
Yes.
I'm sorry, I cannot really speak much Indonesian. So you are from Kyoto University?
Ya, nichu ko senno nichu hachi kokua Kyoto Daike kuno hakusere.
Ah, I see.
But I think you get doctoral degree from Tokyo Daigaku desu ka?
Yes, Tokyo Daigaku, Tokyo University.
Yeah, I graduate after you graduate from Tokyo, maybe tabung. I graduate in 2008.
I see.
Yeah. Yes, nice to meet you, Sensei.
Nice to meet you. Thank you.
Yamaji Sensei.
Hello.
We will start at 1 o'clock p.m.
Okay.
Yes, yeah. For Indonesian time or 3 p.m. for Tokyo time.
Okay.
Yeah.
Kita mulai tetap jam 1 aja Pak Fajar ya.
Nggih, Prof.
Karena di Jepang kan berarti 2 jam lebih dulu kan.
Nggih, di Jepang lebih cepat, Prof.
Iya, lebih dulu ya, jam 3 sore berarti.
Jam 3 sore.
Iya, biar tidak karena kan kita aktivitasnya masing-masing. Jadi, pokoknya nanti jam 1
Sumimasen,
kita
Sensei.
mulai.
Tokyo, thank you do desu ka? Today.
It's humid.
Yes.
Yeah, it's hot and humid, but not too bad.
Okay, wakata.
Maybe we are a little bit concerned about coronavirus. The situation in Tokyo is not so good recently.
Oh, so ka.
How is it in Indonesia?
The temperature today about 32 or 33 Celsius degree. Tabung.
Okay. Yeah, I think it's about the same. So how is it in Indonesia? Can you have classes in rooms, or do you have?
Sumimasen Sensei, your son is not here.
Sorry.
Yeah.
Yeah. So do you have online lectures, or how is coronavirus in Indonesia?
Coronavirus in Indonesia
decrease.
Yeah, it's decreased, let's say.
So do you have lectures in classrooms, or do you have online lectures?
Online, Sensei. Online lectures. Yeah. In Waseda, maybe online too.
Minute ahead.
Menit lagi kita mulai.
Mas Faisal udah direkam ya?
Sampun, Pak.
Faisal, lagu Indonesia Rayanya sudah siap ya Mas Faisal?
Sudah siap, Pak.
Ya, nanti setelah itu saya nanti beri apa ya. Nanti setelah saya beri apa terus diputarkan.
Mas Faisal nggak usah di mute ya, jadi biar kalau pas di biar cepat.
Jadi setelah doa bersama Mas Faisal terus nanti saya bilang the national anthem Indonesia Raya. Itu langsung.
Untuk doanya sudah Pak Fajar ya?
Dalam selesai?
Untuk doanya sudah ya?
Sudah.
Oh, udah siap. Ya, siap.
Hanya doa bersama gitu sih Sensei. Let's pray together gitu aja sih cukup.
Oke.
Hanya doa bersama gitu sih Sensei. Let's pray together.
Suaranya kok double ini, Mas Faisal. Dari mana ya?
Soalnya saya buka YouTube Pak juga, buka YouTube sama Bendik ya. Makanya mending saya di mute aja Pak.
Oh iya, YouTube. Oh ya, oke. Yang penting Mas Faisal ya. Pada saat dipanggil ya. Bisa ya. Oke.
Excuse me, ladies and gentlemen. May I have your attention, please? Our opening ceremony is about to begin. Please have a nice your position. Suara kita dengar nih Pak Prof, ada angin.
Terdengar. Lancar.
Kita mulai. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah, Muhammad wa ala alihi Muhammad. Good afternoon, ladies and gentlemen. Welcome to Zoom meeting. We proudly present the webinar on physics, Division of Radiation and Medical Physics, Department of Physics, Faculty of Mathematics and Natural Sciences, Diponegoro University, 2021. It's being a great honor for me, Fajar Arihanto, to be standing here and welcome each and every one of you in webinar on physics. Ladies and gentlemen, over the next about 2 hours, this meeting will provide you plenty of opportunities to discuss, share knowledge and insights. Before we proceed this program today, we would like to express our sincerely gratitude to Excellency, the head of Department of Physics, Faculty of Mathematics and Natural Sciences, Diponegoro University, Mr. Professor Dr. Hedi Stanto. Good afternoon.
Good afternoon, Mr. Fajar. Thank you.
Excellency, the head of Division of Radiation and Medical Physics, Department of Physics, Faculty of Mathematics and Natural Sciences, Diponegoro University, Mr. Zainul Muhrisin, Master of Science. Excellency of Speaker from Waseda University, Professor Dr. Engineering Akifumi Yamaji. Hello, Yamaji Sensei. Welcome to Indonesia. Excellency, distinguished guests, ladies and gentlemen. Excellencies, ladies and gentlemen, allow me as the host to read the composition of the program as for the arrangement of the program as follows. Number 1, opening, and then welcome speech from Mr. Professor Dr. Hedi Stanto, and then material exposure about multi-level physics modeling for advanced reactor design by Yamaji Sensei from Waseda University, and then discussion and give certificate, and the last is closing. Ladies and gentlemen, before we begin this event, let us pray together. May God make this event beneficial for all of us, and this event can run smoothly and conducively. Let's pray, please. Enough. Ladies and gentlemen, let's sing the national anthem, Indonesia Raya. For Mr. Faisal, please. Thank you. Menuntun pada ragu, di sana aku berdiri dan dipanggil Indonesia kebangsaan, bangsa dan tanah air. Marilah kita bersatu, Indonesia bersatu. Hiduplah tanah negeri, bangsaku rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya, Indonesia Raya, Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Thank you very much, ladies and gentlemen, for the singing the national anthem. Excellencies, our distinguished guests, ladies and gentlemen, without further ado, we would like to invite to the screen to deliver her welcome speech and to officially open as head of Department of Physics, Faculty of Mathematics and Natural Sciences, Diponegoro University, Mr. Professor Dr. Heri Sutanto. For Mr. Professor Dr. Heri Sutanto, this time is yours, please.
Bismillahirrahmanirrahim. Thank you, Mr. Fajar, Master of Science, for introduction. Our Honorable Physics Department webinar speaker, Professor Dr. Engineering Akifumi Yamachi from the Graduate School of Advanced Science and Engineering, Waseda University, Japan, and all participants in today's webinar on physics. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon and ohayo gozaimasu. On behalf of the Faculty of Science and Mathematics, Diponegoro University, we are pleased to cordially welcome Professor Akifumi Yamachi and all participants to the Physics Department Visiting Professor Webinar Lecture 2021. This webinar aims to facilitate brainstorming and state of the art information in physics as one of our goals in the physics department. We hope that the physics innovation of technology can be applied in research and industries to increase the role of science for the community and stimulate collaboration between industries, researchers, and government from community welfare. We sincerely thank Professor Yamachi for your attendance and significant contribution to promoting science and technology at Diponegoro University. We hope this webinar can inspire many scientists to improve their research and open broader international collaboration between institutions. We also sincerely open our door for further collaboration with Waseda University, especially with the Graduate School of Advanced Science Engineering, to enhance physics research and education in Diponegoro University. Suppose Professor Yamachi has a future plan to visit Indonesia, we are honored to invite Professor Yamachi to Semarang, Central Java, Indonesia, where the traditional culture and heritage live alongside technology. Last but not least, please enjoy the webinar, and we look forward to collaborating with Waseda University in the years ahead. Thank you. Arigatou gozaimasu. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Mr. Professor Dr. Heri Sutanto, for the welcoming speech. Excellencies, ladies and gentlemen, now we come to our main program, material exposure about multi-level physics modeling for expand reactor design, who will be led by our moderator, Dr. Engineering Eko Hidayanto. The first of all, allow me to introduce our moderator, Dr. Engineering Eko Hidayanto. He is a lecturer at Department of Physics, Faculty of Mathematics and Natural Sciences, Diponegoro University. For Dr. Engineering Eko Hidayanto, this time is yours. Please, thank you.
Thank you, MC, for the time. Uh, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon and ohayo gozaimasu. Especially for Machi Sensei. Welcome to our department, Physics Department of Diponegoro University. So in Japanese, we can say Diponegoro Daigaku no Butsurikaku e Yokoso, Yamachi Sensei. Today we have the general lecture, and we invite Professor Akifumi Yamachi from Graduate School of Advanced Science and Engineering, Waseda University, Waseda Daigaku. At the first time that MC said, his topic is about multi-level physics modeling for advanced reactor design. But before Yamachi Sensei start his lecture, let me introduce him by read his short biography. That Yamachi Akifumi currently position is associate professor in the Faculty of Science and Engineering, Graduate School of Advanced Science and Engineering, Waseda University. About his education, he got a bachelor, master, and PhD from Tokyo University. As you know that the Tokyo University is the best university in Japan. Ichiban no Daigaku. I graduate from Nibang, Kyoto Daigaku Sensei. Then experience his research is before starting from 2006 2014. He is a research engineer at the Japan Atomic Agency, GIAI. Then 2011 to 2014 as nuclear scientist at the Nuclear Energy Agency. 2014 to 2017 as assistant professor. Then 2017 to present he is associate professor at the Department of Quantum Science Engineering, Waseda University. Then, of course, his research interest is related to nuclear energy, such as reactor physics, fuel performance, advanced reactor, Schaeffer's accident, and others like this. And you get information, and at the Scopus Gogger Scholar, you will get so many publication from Yamachi Sensei. I read the Scopus, each index of his Scopus is 13. Right. Okay, ladies and gentlemen, I also want to introduce about just mungkin 2 or 3 minutes about generation 4 nuclear power plant. That we have 6 generation 4 power plant reactor, like FHTR, SFR, GFR, LFR, MSR, and SCWR. Generation 4 power plant system is very suitable to apply in construction of nuclear power plant in Indonesia, also in other country. That you know, as generation 4 of nuclear power plant is able to produce sustainable energy, then long-term availability of nuclear fuel, Then also generation 4 being able to minimize nuclear waste and reduce the burden long-term management. Also having any advantage in the field of safety and reliability. Also, we can say that generation 4 of nuclear power plant is good prospect if used in Indonesia or other country. I read some magazine or website that generation 4 is if we design in Indonesia from zero to finish until the generation 4 is installed, it's around 2.3 trillion, not 11 trillion. Just only 2.3 trillion. So it's a very good prospect in Indonesia. Okay, not long. I will introduce about this. So please, Yamachi Sensei, give a presentation. Yamachi Sensei, no chikang wa daikangi desu. Dozo, please, Yamachi Sensei.
Thank you. Thank you for your very kind invitation. And let me try to share my screen first. Oh, do you see my screen now?
Yes.
Yes,
Okay.
I can read.
Thank you.
I can read.
So thank you for your very kind invitation, and I really wanted to visit you this time, maybe last year. Actually, we in Japan, we were planning to, as you may know, that we were planning to organize a trip, conferences and trip hosted by the Cabinet Office of Japan, and last year. And in the end, we had to decide to switch to online seminar due to the outbreak of coronavirus. But we were really hoping that we could visit you last year. But never mind. That let's see. I hope we can meet each other very soon in the near future. Hopefully, maybe next year. And so, in the meantime, with the aid of online systems like Zoom, it's my very pleasure to meet all of you. And I thank Professor Heli Stanto and Professor Eko Hideyanto for your very kind invitation, and Mr. Fajera Arianto for your very nice invitation and kind coordination. So thank you very much. And yes, so I see that there are many participants. I suppose quite a few of you are from faculty members, professors, but maybe also some students with probably different backgrounds. So if you notice something, please interrupt me and I can switch my presentation. If you have any specific interests, I can focus on those topics. So let me try to start with my presentation on multi-level physics modeling for advanced reactor design. Oh yeah, before I do that, so here is a map, and I'm from Japan, in Tokyo. So this is where we are located in Tokyo. In the map of Tokyo, I'm from Waseda University, and it's at the very center of Tokyo. And I suppose some of you are familiar with Tokyo, but many of you have not had chance to visit us yet. So if in the future you have the chance to visit us in Japan, Tokyo, then please find Waseda University. It's very at the center of Tokyo. There are like imperial palace at the very center, famous Tokyo Sky Tree that was recently built, and the government is also located in the center. For our university, this is just numbers that describe the outline of our university. We were established in 1882. And actually, we are one of the largest universities in Japan, with over 40,000 students, undergraduates, around 8,000 postgraduates. And we actually also have many international students. And from Indonesia, we have, as of 2019, we have just about 100 students from Indonesia. So actually, I do have some students in my lab too. So it's very nice to see you all in Zoom. And there are 10 faculties, and one of them is the Faculty of Science and Engineering, which I'm located. And 18,000, I'm sorry, 1,870 faculty members. So that's the kind of size of our university. For the research, so I will be, I'm very grateful that you invited me to talk about advanced reactor design. Basically, I work in the field of reactor systems. So designing reactor systems and analyzing reactor systems. And so most of the talk today, I will try to focus on advanced reactor design. Maybe a little bit on the fuel safety, but I also work very much on severe accidents of reactors, like what happened in Fukushima in 2011, and some simulations such as particle methods. So here is my outline that you have already kindly introduced, so thank you. So if I go into the contents of my presentation today, I have prepared some slides, basically two sections. One on introduction to core design, reactor core design. So maybe for professors, this may not be so new. It's introductory to core designs, reactor physics, reactor thermal hydraulics, and for field performance. And then part two is on brief introduction to advanced reactor design, but I specifically picked up on what I know best, which is supercritical, like water-cooled reactor. So I will be talking a little bit about SCWR. I have picked up some example like minor actinide transmutation with SCWR. So let's see if I can arrange my presentation in a good manner. So if I start from the beginning, let me start with introduction to core design, reactor core design. So what is core design? You can design anything. In engineering work, you design cars, you design computers. So I am now talking about designing a nuclear reactor core, but maybe I should say conceptual design. So in concepts, for designing a reactor core, we have design targets. There are many design targets, but I have just picked up the the dominant targets, which is, of course, we want to generate electricity. So that's our main purpose. Of course, there are many different ways for utilizing nuclear reactors, but primarily we want to generate electricity. That's the one. Another thing is we want to utilize our uranium resources as efficiently as possible. So we don't want to waste uranium resources. So if I pick up two targets, then these are the main two targets. In the counterparts, there are always some criteria that you have to satisfy if you want to design a reactor safely. And these are the design criteria that's often considered first in conceptual design stage. So these are the reactivity control, that's reactor physics, heat removal or transport, that's thermal hydraulics, and the confinement of radioactive materials. So that's field performance and management. So in reality, these are actually very complicated. There are complex interactions between evaluation of electricity generation, power generations, evaluations of fuel depletions, and evaluations of safety, that is reactivity control, heat removal, confinement of radioactive materials. So I will try to, today, I will try to break down these relationships in terms of reactor physics, thermal hydraulics, and fuel performance in the next, maybe next 10 or 20 minutes. So this is very fundamental. So I will be boring some of you. And if you are not familiar with this, then you can get on this. There are three items that I will be talking. Reactor physics is, so number one is reactor physics. And this is explaining basically what is simulated in reactor physics calculations in a reactor core. I assume that everyone knows that in the reactor core there are fuel rods looking like this, which contains uranium fuel inside. And this is just a zoom up of 4 fuel rods. And essentially what's being calculated in these simulations is tracking the reactions and transport of neutrons. The neutrons trigger reactions like fission reactions, but that's not the only one. Here, this is conceptually showing what kind of reactions may happen if neutrons interact with. There are other reactions like capture, scatter, and so on. So basically what we do in these simulations is that we track neutrons and reactions that happen with the transport of neutrons. And what we want to evaluate with these simulations is relationships between criticality. That means we want to maintain chain reaction efficiency at a given constant rate, and we want to be able to control such reactions. In another word, we want to make sure that there is always negative feedbacks to the reactors if any reactivities are inserted to the core. We don't want the core to explode in a easy manner. So here is describing what I mean by reactivity control. This is explaining about the requirements that a reactor core has to satisfy so that a reactor can operate safely without overshooting the power. So maybe the figure is not so good. On the left-hand side, I'm showing nuclear fission generating neutrons, which will trigger another fission. On the right-hand side, the same figures, but the situation is a little bit different. On the left-hand side, the power is low. The coolant in blue is water. If the power is increased, we tend to generate void What I mean by void is bubbles, gas bubbles. So what happens if we increase the power of the reactor from low power to high power? We generate gas bubbles, steam bubbles in coolant, and this will give feedbacks. Maybe I don't have time to go into too much details. But there are different feedbacks that I have listed here. For example, feedback number one is that the
mainnya di
neutrons
situ kebanyakan.
moderation is reduced. That means neutrons generated in low power state, they collide with hydrogens in the coolant, H2O. If you collide neutron with a hydrogen, the speed of neutron is reduced. This is neutron moderation. If I increase the power, there will be gas bubbles, and so such collision will be reduced. And then this will lead to less thermal neutron, and actually this will give negative feedbacks. Negative feedback means the reactivity is reduced. That means fission reactions is less likely to happen under this condition. So similarly, there are other feedbacks like neutron leakage is reduced. That means more I'm sorry, this is wrong. Neutron leakage is increased. I made a mistake here. Neutron leakage is increased. So there will be less neutrons in the
Pak
core,
Zumron
which
itu
will be
hilang
negative
semua
feedback.
kuncinya. Pak Zumron kehilangan kunci.
What we want to make sure in our
Udah
reactor
ketemu
design
terus hilang
is
lagi
that
sama Pak Zumron.
finally, with these combinations, there are negative feedbacks and positive feedbacks. If we evaluate all of them, we make sure that everything will come out negative. If you put power, there will be a break. There will be a resistance that suppresses increase of
Pak
the
Zum
reactor
tanya
power.
saya, Mas, nggak
So
ngulangi kunci saya?
that's the basics of reactivity control. Part 2 is thermal hydraulics. So this may be much more easier. Basically, you generate heat. You want to be able to transport heat so that your fuel does not burn out. This is a photograph here is showing you create boiling. If I increase the heat flux of the rod,
Pak Zum pas bukuin itu kan
at
Pak
some
Zumron
point
belum
there will be
nasional bener, Mas. Nggak
boiling
kunci saya,
transition.
Mas.
That will
Tadi pagi sama kemarin sih baru aku kampus.
prevent or deteriorate the rate of heat transfer from the fuel rod to the coolant, and you will see burnout of the fuel rod. This is still boiling. So we don't want that. This is typical textbook explanation, so maybe I should not go into much to get you bored on this. But basically, if you increase heat flux, at some point, you will no longer be able to remove heat efficiently, that your heating rod will burn out to a very high temperature. And then, obviously, if your reactor core experiences boiling transition, you cannot cool your core, and you will damage your reactor. So that's not what you want. So this is kind of evaluations in reactor thermal hydraulics. So I have talked a little bit about reactor physics and reactor thermal hydraulics. And these are actually coupled. This is showing some conceptual relationships that in a reactor core you have fissions. Fissions are controlled by neutrons, and this will give you reactor power. With this power evaluations, we perform thermal hydraulics analysis to make sure that the heat you generated with fission reactions to make sure that the heat is removed, and this will give you the temperature distribution in your core. Now, once the temperature distribution is given, then you know the status of your coolant boiling situations in case of boiling water reactor. And this will give you a feedback to the fission reaction calculations. So these calculations are combined. This is the concept of coupling of neutronics and thermal hydraulics, which are particularly important when you have light water cooled reactors. For some reactors, these couplings are not so strong. There are reactors which have strong couplings and weaker couplings. If you are talking about water-cooled reactors, like in Japan, most of our reactors are cooled by water. And this is a very important relationships between the reactor physics and thermal hydraulics. Okay, the third part is a little bit different, but it's very important. That obviously you don't want to damage your reactor fuel. So the third one is fuel performance modeling. And basically what you want to evaluate here is that your fuel rod is not broken. It doesn't break. That's what you want. So then we need to know how a fuel rod may break. And this is typically in light water cooled reactor core. The typical failure of your fuel is what we call pellet cladding mechanical interactions, or we sometimes call it PCMI. And the mechanism of PCMI is it's not so complex. Basically, you have a fuel pellet, which is made of uranium dioxide, UO2. This UO2 pellet is enclosed in a metallic tube, which is cladding. We call it cladding. So, if your fuel pellet, maybe okay, this one, okay. So, how do we define a mechanical failure of fuel rods? This is a picture on the right-hand side. It's showing some test results, not from commercial reactors, but from experimental reactors, that the fuel rods have failed. And basically what happens, if you increase your power too much, then you will have melting of the fuel pellet at the very center. And this will cause volumetric expansion. And the pellet will interact with the cladding until it fails. So this is PCMI failure. So that's what you don't want. Okay. Is it okay? Okay. I go on? Okay. So this is summarizing what we tend to consider, what we generally consider for designing a reactor in conceptual design. We start with a design target. We evaluate the global core power distributions. I didn't explain into details, but there are global power distributions, local power distributions. There is engineering uncertainties. Then we can evaluate the design limit of your reactor. That's the very limits that you don't want to exceed in normal operation. From that state, we evaluate safety, abnormal transients or accident analysis, and of course, we cannot test our commercial reactors in that way. So we do experiments to confirm that you do not break your fuel rods. That's what you want. So once you have experiments, then you have a feedback to your design targets. And this is a kind of iterations between the design target, design limit, design criteria, and experiments. And what connect between these findings is simulations. You need multi-level physics simulations, like vector physics, thermal hydraulics, fuel performance. These are some examples. And by this way, we can develop a reactor concept. So that was maybe the first part of my presentation on a relatively a very maybe too much basics, but the fundamentals of conceptual coordination. Now, if I go on to the second, I can take some questions at this point. If you have any questions, maybe I can stop at this point before I go to the next part, or I can just simply proceed. Should I proceed? Okay.
Silakan bagi yang ingin menanyakan barangkali bisa menyala. If any question, please ask directly to Zamashi Sensei, or you can write in chat room.
Yeah, I can see the chat too, but maybe I cannot quite read.
Okay. Yes, Dr. Sensei, please go through.
Okay. Okay, so let me go on and let me finish first, and then we can maybe discuss if anyone wants to discuss on any particular topics. So now I have talked too much about concepts, but maybe everything is conceptual at this point. But let me go on to generation for reactors. As already introduced today at the beginning, there are 6 reactor concepts in generation for reactors. And I will be talking today about supercritical water-cooled reactor. Actually, the generation 4 was formed in, I think, roughly in year 2000. And I was a student at that time when these frameworks were being developed. So it was very exciting at those days. But anyway, so there are 6 different reactor concepts. Basically, all reactors have different reactor coolant. If you compare the reactors, of course, all reactors operate by nuclear fissions. Some of them have different fuels, but the characteristics are that they all have different coolants, like sodium or lead cool, or here it's supercritical water cool. And this is the only one among the 6 that uses water as a coolant of a nuclear reactor. Okay, so this is very simple explanation, simplified explanation of supercritical water. Here is a conceptual diagram that describes typically 3 states of water. That's ice, water, and steam. Solid, liquid, gas by temperature and pressure. So that's normal. What's not so familiar maybe to some of you is that if you increase pressure and temperature to a very high state, here I pointed out the critical point, which is 22 megapascals and 370 degrees Celsius. So beyond this point, we have what we call supercritical state. And so what is supercritical state? it's basically a state where there is no difference, no distinguishable difference between the liquid and gas. That's strange, right? Here is some picture. Actually, you can check on YouTube to show some movie. This is not water, but CO2, carbon dioxide. That's a very simple experiment which shows what supercritical state is. Here in the picture, we can see if there's a liquid at the bottom. On the upper side is gas, CO2. If we increase temperature and pressure beyond this critical point, then there will be no difference between the gas and liquid. And now you can see there's no phase, interface between the liquid and gas. So that's what's described in here. The figure on the right-hand side, the bottom right, this graph is another way to describe if we show density of water against temperature. Obviously, if you boil a water, you will suddenly drop the density from water to steam. So this is very normal, boiling if the pressure is 7 megapascal. Now, if we go on to supercritical pressure, here its example is 25 megapascal. We no longer see sudden drop in density. That means there is no boiling. So this is explanation of supercritical water. So what's good about using supercritical water for nuclear reactor? This is just summarizing some features of supercritical water reactor. Basically, this is a reactor concept that's based on the old generation 2 light water reactor technology combined with the latest fossil fuel power plant that operates at supercritical pressure. There are 4 features: simple and compact plant systems, high thermal efficiency, utilization of current technologies, and flexible fuel management. I will briefly talk about these 4 features in the next few slides. So feature number 1, simple and compact once-through direct cycle system. This figure is describing the reactor system of SCWR. The reactor core here, the turbine, condenser, and pump. So that's the system. And what we mean by once-through direct cycle, it means that the reactor coolant that exits the reactor pressure vessel directly enters the turbine, condense, and go back to the reactor core. So that's quite simple. Actually, if you compare with other reactor systems, you can see that the systems are quite complex in these other reactor systems compared with SCWR. So this is one of the features that there is no boiling of a coolant. If you somehow generate a steam-like coolant that exits the reactor pressure vessel, enters the turbine, drive the power turbine, generate electricity, and come back to the reactor system again. So this is the feature of one-through direct cycle system. The balance of plant, meaning the turbine system, is similar to the fossil fire power plant. Maybe I can skip some of the details here, but specific enthalpy of the steam flow is low. The number of steam lines can be reduced. High-speed turbine pressure, high pressure turbines can be used, and so on. These may be some minor points. what is the major point is that the system
Oh,
is simple
nama.
and compact. This is to explain, give you some additional explanation for the simple plant systems. These two figures, maybe some of you are familiar, some of you may not be so familiar, are the systems describing the current commercial light water cooled reactors.
Oh,
There
yang
are two
IZ itu loh,
types
Pak.
in worldwide. Many countries operate pressurized water reactor, or PWR, which is the figure on the right-hand side. In Japan and some other countries, there are boiling water reactor, BWR systems. So these two reactor systems. I will not go into the details of these reactor systems, but what I want to
Oke, sampun, Pak.
emphasize here is that in
Kok raiso ya?
both of
Maksimal
these
4 ya?
reactor systems, you will always have some
3.
coolant to boil. Obviously, if you want to generate heat, you want to
Ya, wingi
remove
iso
heat
akeh. Wingi
and
iso
generate
8.
steam, you will have boiling. And at some point, somewhere in your system, you will always have liquid water that floats together with
Iso ada maksimal.
steam.
Ini kayak maksimal 3 nggih, Pak, kohosnya, Pak.
So, but the turbines can accept only steam. Turbines cannot accept water. So what it means is that you will need some equipment or systems that separate steam from water. So that's the fundamentals of these reactor systems. And that's one of the reasons why these reactor systems are so complex. You have to separate steam from water. Okay, so that's not necessary in supercritical water reactor. So that's feature number 1. Maybe I don't want to go into too much detail for the others, but feature number 2, high thermal efficiency. Basically, I believe many of you are familiar with this principle that if you basically have high temperature, you can get higher thermal efficiency. The figure here is just showing a relationship between the main steam temperature and the thermal efficiency of the plant systems. And basically, the hotter, the higher the temperature, the higher the efficiency. For SCWR, the typical design is between 500 degrees to just about over 600 degrees Celsius, corresponding to the efficiency of 44 to 48%. You might think this is low or high, depending on which kind of things that you normally work with. But if I compare with the current commercial light water cooled reactors, these are between 33 and 35%. So that's the kind of difference between current commercial reactors and generation for supercritical reactor. Feature number 3 about utilization of current technology. So nuclear is very difficult area that you cannot easily jump from a technology level 1 to the next technology with a huge jump. We want to utilize our current technologies. So basically, this system uses water. That's the best. That's the best. We know water. Everyone knows what water is. In any industries, everyone uses water. So basically, the industries are familiar with this water system. Utilities, they are also capable of managing the system because many vendors of light water reactors, nuclear reactors, they actually also make supercritical fossil fuel power plants. And the utilities that operate reactors they also operate the supercritical fossil power plants. So there is a good background for developing such technologies. The last one, feature number 4, is flexible fuel management. This may not be so easy for the people without the good background, but basically, as I talked earlier today, that there is a strong coupling between the reactor physics and thermal hydraulics. The reason behind this is reactor physics is quite sensitive to coolant density because hydrogen atoms collide with neutrons. So what happens in supercritical water reactor is that the coolant density changes very much within the reactor system. As the result, here this is showing neutron spectrum. Maybe not so familiar to some of you. Basically, it's showing how much neutrons there are against the energy of neutron. And this is like characterizing reactor physics of your reactor. Two typical reactors. One is what we call fast reactor. Here, SFR stands for sodium fast reactor. It means the reactor systems operate with large fraction of high energy neutrons. Here is another one, LWR, that is light water cooled reactor. And this one is showing that the reactor system operates with relatively low energy neutrons. The supercritical water reactor is actually in between. This is very unique. And so there are features of fast reactors and then features of thermal reactors, light water reactors, both in the same reactor system. So that's feature number 4. Okay. So from here, maybe I can relatively go quickly. Research issues for SCWR, plant concept, core thermal hydraulics, materials, and corrosions. But today, I can only talk about core design, thermal reactor, or fast reactor. Okay, some examples of the research. I actually found some histories, and these are, I think these are the very beginning of generation for light water cooled reactor. That goes back as old as 1957. This was only conceptual, but the Westinghouse in US proposed the design to cool the reactor system with supercritical light water. With a moderator, I didn't explain here very much, using the normal light water. Other designs. So here, 1957, 1959, 1962, these were the era when these reactors were proposed. But they were never built. The one that was only built is not quite supercritical, but it's a superheater, BWR type superheater that was first operated in 1969. So this was built. So this was rare. And it had some superheater that heats up the steam to superheating state. So this was the only reactor for test reactor. Now, in the current research, there are different families of supercritical water reactors in Canada, China, Europe, and Japan. So there are four major groups in the research of SCWR with quite some different design concepts. These figures on the bottom are showing the fuel lattice, fuel rods arranged in these manners, or sometimes these manners, with some boxes, and these boxes contain some water that provides neutron moderations. That means neutrons colliding with high density water inside these boxes. So anyway, 4 different reactor system groups, and Japan is one of them. I have picked up one topic, just one, about the minor actinide transmutation. So if you are from physics department, maybe you are very familiar with these kind of things, but we have uranium and plutonium in the periodic table. And these are the elements that we call minor actinides, meaning actinides, but not the major ones, but the minor ones. But they are called minor, but they are actually quite important. They are highly active and long life. So after using the reactor, the spent fuels have to be disposed, but they are highly radioactive. And the reason for that is because they contain a large amount of minor actinides. The figure here is showing toxicity against the years after discharge of the reactor in log scale. So one of the reasons for the society to be not so confident with nuclear reactor is because you have spent fuels that are highly radioactive for long years. And one of the reasons is because of the high content of minor actinides. If we could separate minor actinides from the spent fuel, then this is the red figure, the red line here shows that the toxicity can be as low as, I didn't put it, but can be as low as the natural uranium within a few hundred years. So that's good things. So separating minor actinides from spent fuel, we can shorten the time for the spent fuel to be reduce the radioactivity. Okay. Do I have some questions? Okay. Safety. Reactor safer than other reactor to subshells.
Oke, saya tidak.
So I'm not sure if I have picked up the question very well, but the question is about comparing MSR, molten salt reactor, okay. I'm not sure about the question, but if someone could, if you could explain about your questions, maybe I can answer better.
Just a moment, Sensei. Maybe his question is about, he want to know about comparison between SCWR and MSR, where the MSR cannot stable in the high temperature, and how about STWR? And how about the safety for? How about the safety between SCWR and MSR, like this? Maybe like this question.
Okay. Okay. Let me try to answer. Different reactors have different safety characteristics. For example, maybe not MSR. Yeah, MSR or sodium fast reactors. They operate at relatively low pressure, low operating pressure
Jakom
systems.
sih deh, bagus. Jam 11.
The fundamental difference between low pressure operating system and high pressure operating system is loss of coolant accident, or if you have a breach to your reactor pipes, you have pipes. If you have high pressure system and if you have a break in the pipe, you will lose your pressure. And once you lose your pressure, typically for water-cooled reactors, then you will have water boiling. Obviously, at atmospheric pressure, the water boils at 100 degrees Celsius. That's the fate of water. You cannot change this. If your pressure is atmospheric pressure, then your coolant will always boil at about 100 degrees Celsius. That means you face the risk of losing your coolant. So that's the nature of your reactor system. So you have to be prepared. Your system has to be prepared for the case where you lose your pressure. If I talk about like sodium fast reactor, that doesn't happen. If you break a pipe, you don't lose any pressure because your pressure is already low. So your coolant will never boil, and that's too much. But it could boil, but normally it doesn't boil. But then there are other risks. For example, sodium. If you have sodium with water in direct contact, then you will have very vigorous chemical reactions. So different reactors have different safety issues, and it's not so easy to say which reactor is safer. But what you have to do is you have to know the safety characteristics of your system and be prepared for that specific reactor safety issues. I'm not sure if I answered to the question there, but basically, the concern for any water-cooled reactor system is loss of pressure or loss of coolant. And this was actually issue in the Fukushima accident in 2011. It's not quite the case. It's a little bit different, but anyway, the loss of coolant is major design accident, design basis accident. That's the one. Did I answer well?
Okay, this question from our master student, Miss Neneng Triasana. Maybe Neneng Triasana is here. You can ask directly to Yamashi Sensei, please. Ya, silakan Mbak Neneng kalau mau menanyakan lebih lanjut bisa ditanyakan. Neneng Triasana ya tadi ya, Neneng Triasana ya.
Sudah cukup, Pak.
It's enough, Sensei.
Is it okay?
Nggak tahu.
Maybe you will continue this your presentation, or some student will ask. It's okay.
Yeah, the remaining, I don't have many more to remain, so I could go on, but yeah, I'm happy to receive any questions at this point. Shall I go on?
Yang lain silakan. Other participant, please, if any question. So I get a message from our student. If our student will he or she will wish get master or doctoral degree in your university, what the procedure for to get scholarship from your university, or Mon Buka Kakuso maybe, or other scholarship, or maybe you sama Ci Sensei can give some information to study on your university, especially on your department. Please, Ci Sensei, if you have information.
I see. So typically, I think I forgot the name, but I see most students from Indonesia to get the Indonesian scholarship, the government's scholarship. In Japan, there are a few funding for scholarship for international students, but they are very competitive.
Oh, yeah.
And so most international students get scholarship from their own countries before arriving to Japan. And what I normally do is I always write recommendation letters, but I can also write the research plan, so typically I help applicants prepare research plan so that the applicant can be competitive in their own countries to win their scholarships. That's the way I have been doing for students from China, a student from Indonesia as well. And so far, it's been quite successful. And so I don't recommend trying to get Japanese scholarship after you arrived to Japan. That's quite uncertain.
Yes, Wakata. But we have like LPDP scholarship from my country. But in my country also student it's very competitive to get scholarship. If we can get the scholarship, can you or other sensei accepted our student to study in your university? This scholarship from my country, LPDP or others?
Yeah.
Okay, sensei.
That's fine. Yeah. So LGBT scholarship is I think quite well known at Waseda University too. So we have a like entrance examination for doctor course students, but it's like interview. So it's application by documents and sometimes interviews, but no no written tests. But so we require some CVs. I can like, if there is a specific case, then we can maybe work on that applications together. But typically, CV, I forgot the details, but the CV, yeah, CV and your past research experience and so on.
Oh, yes. Okay, I understand. Silakan yang lain, other participant can ask. to Sensei. Just a moment. Maybe there is a question.
Okay, that's good, reactors. Yeah, typically like CO2 or helium gas, that kind of inert gas is used for gas cooled reactors.
Then there is a question from no name. Excuse me, Sensei. I want to ask what kind of gas that used in the cool fast reactor and how it works. Sensei. Sensei also can read on room chat room.
So normally like CO2, carbon dioxide, or helium, He, that kind of inert gas is used for gas cooled reactors. Not active, not non-active gas. Yeah. And for these gas reactors, that's fine because you simply heat up the gas from low temperature to high temperature. So maybe the drawback is your core power density is not so high because the heat removal by gas is not as efficient as by liquid or boiling liquid. But anyway, generally inert gas like carbon dioxide or helium, that's typically used in gas cooled fast reactors.
Okay, Sensei. Mungkin Pak Fajar Sensei also can ask directly to Yamachi Sensei. Silakan Pak Fajar. Okay. I also want to ask to Yamachi Sensei. As you know, and we already know that in Indonesia there is no nuclear power plant till today, and how many years ago some of scientists asked to our government to build the nuclear power plant, but it's not agree until now. In your opinion, what is should be prepared to build the nuclear power plant? So we can give suggestion to our government. Maybe Yamachi Sensei can be get information to me, to us.
That's very difficult question. I think many countries have different reasons for either proceeding with nuclear or not proceeding with nuclear, and I see that in many countries safety is one big concern. Another concern may be large investment. What I have been seeing recently is that not many companies or private companies cannot afford to invest on development of nuclear power reactors because of large uncertainty. So generally, any countries that want to introduce nuclear requires large support from the government, but the government doesn't have much funding itself either. So this is, I think, a large drawback. And the recent, maybe a trend, is to try to see the possibility of introducing small modular reactors. So the reactor system itself is not so large, the power is not so large, but the investment is not so large either. So
With the most with the most ration from my people is about safety from radiation. How opinion about this? The safety from radiation. Yeah, demonstration of my people. If we build the nuclear power plant is because of the safety from radiation. How about that? And your opinion?
Yeah. So again, that's very difficult questions, and is it about the power station itself, or is it about the spent fuel? So then, the radiation concern is always is with the nuclear, but it is with the power station, and it is also with the fuel reprocessing, if you reprocess or disposal. So different sections of nuclear that may trigger concerns of your society. I guess, yeah, it's a difficult question. Maybe I lost voice.
Tentang
it's
silakan
back.
Pak Fajar. Yes. Silakan Pak Fajar kalau ada yang ingin ditanyakan.
Sumimasen.
Okay.
Yamachi Sensei. Okay, thank you for the change. Yamachi Sensei, I have the experience for modeling modular reactor spinor using MCNP, Yamachi Sensei. Maybe can we modeling for the other reactor? For example, molten salt reactor, maybe.
Yeah. So reactor physics is actually not so difficult. As long as you know the fuel contents and coolant composition, fuel and coolant compositions, then you can simulate with relatively good accuracy. The difficulty may be more with thermal hydraulics. That's quite dependent on the reactor system design and the combination of your coolant in the field. Yeah, but the reactor physics is not so difficult. It's just the same simulations are the same.
Thank you, Yamachi Sensei. Arigatou gozaimasu.
Yang lain silakan. Other participant please to ask or give a comment to Yamachi Sensei.
Ada pertanyaan tuh Pak Eko dari Pak Anam.
Oh, yang mana?
Di chat box.
Mana ya? Chat box ya, sebentar. Udah ada Mas Pasar?
Ada.
Di mana ya? Oh yes. This question from our lecture also. Yamachi Sensei, Anam Sensei asks about there is a view on nuclear power plant. They always refer to accidents such as in Chernobyl or Fukushima Daiichi. How to convince to the society that nuclear power plant is safer than a conventional power plant?
Yes. That, honestly speaking, I don't have an answer. I have only suggestions. So here, I was about to talk about this too, but here is some description that I'm asking myself. How safe is safe enough? The figure here shows the fatalities, the number of fatalities, and the frequency per year. And you can see that the figure is quite old and not so good to see, but you can see something natural disasters like earthquakes, tornadoes, hurricanes. These are here in log scale. In down here, 10 to the minus 4, 5, 6. This is the range. And I have two lines. One is meteorites. Meteorites hitting the earth, killing people. So that's the kind of frequency that you expect. And if you compare this line, another line here is the fatalities expected by operation of 100 light water reactors. So here you can see that the probability is about the same. The risk of a meteorite hitting the earth, killing people, is about the same as 100 light water reactors operating and killing the people. And in my view, this figure doesn't help. This figure does explain the risk, give you some numbers, and the scientists, we understand the risk, but the society, our community never accepts this explanation. So we, as an engineer or as a scientist, we will be, for our everlasting research, we will be reducing this probability as low as possible. The ultimate goal is 0, but it will never be 0. But we will be aiming for 0. This will be a never-ending research. But at the end of the day, no matter what the number here is, I don't think the society will be convinced solely by this number. We need a different approach. Together with this is very important. We have to reduce the risk as low as possible, but that's not sufficient. Things like the trust between the scientists and the community, this is very important. It's not easy to develop. And once you lose this trust, it's very difficult to rebuild. That's what's happening in Japan. We have once lost the trust of the society or community because of the accident in Fukushima in 2011. And this will take long time. So there is no answer, but one thing for my research, for what I can do as a professor at the university, what I can do is to improve our understanding of what may happen. Before Fukushima accident, no one knew what will happen. We knew, but we knew very little. We only had very broad understanding. No precise understanding, large uncertainties. So here is typical analysis, severe accident analysis of light water reactor. Basically, the reactor system is modeled by computer program with a node junction model. We give some scenarios, what may happen. We will show what may happen by developing the stories, different events. This is what we call event tree. And we perform the analysis. The movie here on the left-hand side is not by myself. I am using the code developed by US
Aku
NRC.
takon soalnya
It's
mau
called Melbourne.
pacify kan.
But this is the state-of-the-art simulation of severe accident. Of course, I'm just showing the reactor pressure vessel. But you can see that this simulation is so primitive. The reality is far from this. Of course, it does help us understand. It does show some important features of what may happen during severe accident. But this is still very primitive for different reasons. So in my research, as a university researcher, what I can do is to give, with the development of simulation techniques, with the development of computation power, I can apply different simulation techniques. Here is an example that I'm showing is particle method. It's a Lagrangian-based computation fluid dynamics method. So now what I can do is, for example, working on different stages of core degradation. What may happen if the fuel melts during the severe accident in much more details than what used to be simulated in severe accident analysis codes. And of course, the point here is that we cannot do experiments. Many phenomena expected during the accident of the nuclear reactors, we cannot do experiments. It's too dangerous, it's too large, it's too hot. So simulation is one solution. That was not so sufficient in the old days, but now, because we have much more powerful computation power and advanced simulation techniques, this is new area that we can apply at universities. And this will give you much more deeper understanding of what may happen. So we will do our best, our never-ending research to make sure that it will never happen, but it will be never zero. The probability cannot be zero. If so, then in parallel to our effort, we have to deepen our understanding of what may happen, if it must happen. And this is the area where universities can work on. There are many new simulation research, new science that we can work on. I think, but after all, to answer your question, I think the bottleneck or the critical point is the trust between scientists and your community, and that's very difficult. And as a scientist, what I can do is do my best and show everything that I know. But interactions between the community and the scientists, this is the key. I think, I'm not sure if I answered to your question, but it's a very difficult question.
Thank you, Yamachi Sensei. I'm sorry. Is there any your PowerPoint to be presented or already finished, Sensei?
Yeah, actually, this was actually my last presentation slide,
Oh.
and this is my summary.
Mm-hmm.
So, designing the reactor system requires multi-level physics modeling. Today, I talked about reactor physics, thermal hydraulics, and field performance modeling for design. And the one that I just showed now is that recent advances in computation power and tools can enable us to apply simulations to see what may happen during severe accidents of nuclear reactors. So, yeah, thank you for your kind attention.
Arigatou gozaimasu. Yamachi Sensei. It's Kiyomi Bukai presentation. Really, Hontoni, arigatou gozaimasu. Ladies and gentlemen, Yamachi Sensei has already finished his presentation. So I will close the session. If any question, you can ask by email to me or to Mr. Fajar, and Mr. Fajar will send to your question to Yamachi Sensei. Okay, for the last time, again, I would like to thanks Profesor Kifumi Yamachi for
Pertanyaan, Pak Eko.
Oh, ada pertanyaan?
There are some question.
Also,
on
please,
the chat
if
box.
any question. Oh.
Lately there is an issue.
Sorry.
Yes.
Just a moment. Ada pertanyaan ya, sebentar.
Yeah.
Kedua lagi pertanyaan.
There is an
Sorry.
issue.
Oh, sorry, Sensei. There is a question from Muhammad. There is an issue about using more environmentally friendly energy. Could SGWR nuclear develop to be more environmentally friendly as good and safe energy source in the future, Sensei?
Yeah, all the questions today are very good questions and difficult to answer. But one for nuclear, I think the problem is spent fuel. It's fine up to the operation of reactor system, but what to do after you have used your nuclear fuel in the reactor, or you discharge it, and where do you put it? That's a big question. And in Japan, our official strategy is to reprocess. That means we separate the spent fuel to make a new fuel, and so that the amount of fuel that has to be disposed is as small as possible. That's one way. Today, I also talked about minor actinide transmutation. So that's one way to be environmentally friendly. Yeah, so I guess reprocessing is one solution. And of course, accidents. Once you have accidents, then your environment is severely damaged. So that should not happen. And maybe a smaller reactor. In the old days, we always wanted to design a large reactors, but that will also have large impact on the environment. So maybe medium-sized to small-sized reactors might be more affordable from the viewpoint of the environment, the local environment. Yeah, that's all about I could answer today.
Okay. Then again, one question from Anam Sensei, Dr. Anam. He would like to get information about new reactor design. Is different from the previous one, such as in the Chernobyl reactor and is safer. How about it, Yamaji Sensei?
Chernobyl is actually very a unique accident. It's actually the design was wrong. I think the design was wrong. Today I talked about reactivity feedback, and Chernobyl was designed in such a way that when it is operated in the condition that the accident happened, it had a positive feedback. It means that any perturbations to the reactor will exert power, and this will give another positive feedback, and then until it exploded. So actually, apart from Chernobyl, and even at those days, no other reactors could be exploded in that way. So I think we should distinguish Chernobyl accident from the advances of reactor design or reactor safety. I think the recent the main concerns of nuclear power, especially after Fukushima, is about managing decay heat of nuclear fuel after the reactor has shut down. So that's what happened in Fukushima. So we can always safely control the reactor while it is operating. We can safely shut down the reactor. That's fine. But after that, there is still decay heat that's being generated in the reactor. And we have to remove this power. It's only 7% of the rated power after the core has shut down. But it's still large enough to melt the core if you don't have power to cool the reactor. So for light water reactors, typically, especially after the Fukushima accident or even before the accident, there has been generation 3 plus reactors. Today I talked about generation 4, but there is generation 3 plus reactor, which is a minor modification of generation 3. And basically, these reactors are designed in such a way that no one has to do anything for 72 hours after it has shut down to cool the core. So basically, there is large amount of water reservoir that can be injected into the core without the need of electricity to pump the water into the core. For example, we can use gravity force. If you have a large amount of water above the core level and open the valve without using electricity, then you can inject water into the core. So that's one way. And even before the Fukushima accident, it's the fate of the old reactor that the Fukushima accident happened to the reactor that was built in, I forgot which year, but it's generation 2. Most reactors that operate in the world now is generation 3. Generation 3 plus is minor modification of generation 3, but they have features such as 72-hour standalone safety. Meaning that you don't have to do anything for 3 days. You can sit back, relax, and wait for the things to calm down and prepare for things while the system just helps itself to cool down.
Yeah.
Okay. Again, maybe the last one. Mr. Panji will ask directly to Yamachi Sensei. So please, Mr. Panji, you can ask by directly to Yamachi Sensei.
Thank you very much, Mr. Eko Hidayanto. Good afternoon, Sensei. My name is Panji. I am a lecturer in the physics department. I want to ask some questions regarding with your presentations. It's quite interesting research and also interesting physics background to make a model about the nuclear reactor. My question is maybe on behalf of our students who maybe some of them are interested to study deeper about the modeling. I want to know about I want to know whether this research is a part of curriculum in your graduate in your graduate school, or is it or this research is a part of your laboratory, meaning that if our student wants to learn deeper about the knowledge, what graduate school should they enroll, especially in Waseda University, and then what kind of background should they have before enrolling? Because well, in our undergraduate program, we also have a computation course, but the background is only we study a MATLAB program, and by seeing your computation modeling, I'm sure the background, the technical background to build those model is more than a simple computations. We would like to know maybe is there any sophisticated modeling programs that we need to know, or we need to have before we enroll the program, or perhaps we will study in Waseda University. Maybe you have some insight for us. Thank you very much, Sensei.
Yes, so thank you for your question. So I come from the Faculty of Science and Engineering, and actually there are three schools, three graduate schools. And these are the fundamental science and engineering, creative science and engineering, and advanced science and engineering. So they look the same, and they actually, I don't know what the differences are, but I belong to the advanced science and engineering. And in this graduate school, we have what we call cooperative major in nuclear engineering. So that's the nuclear engineering department, where we give lectures for nuclear engineering. But unfortunately for the master students, the lectures are given in Japanese. So until now, all the students I have had from international students, they only joined us for doctor course. For master course, you need some Japanese to understand the lectures. Yeah, so that's probably a difficult point. Otherwise, for research, it's fine as long as we can communicate. Of course, if you have some good background on reactor science or numerical modeling or computer programming, like C++ or the old language it's still used, it's Fortran. These are typically used in the computer codes that I showed today. But that's not mandatory. So if you have a good background on science and engineering, it's better that you have some background on computation programming, but it's not mandatory. Yeah.
And then, but is there any courses or maybe like a training in the Waseda University if our student wants to join the doctoral programs with a limited computational background? Is there any some training for that, or do they need to struggle with the program, especially with the C++ program? Because it's I know a little bit C++ program, and based on my experience, that is quite a tedious job
I
to
see. I
learn.
see.
Okay. And we have some.
Well, typically it's a kind of on-job training.
Okay. Yeah.
So there are students that work on all the simulations I showed today are by students,
Okay.
and they have good. They learn most of them come join my lab with almost zero knowledge of these simulations, but they quickly pick up. And we work together, like everyone. Well, it's difficult today because of coronavirus, but everyone sits next to each other and learn every day. So yeah,
Okay.
it
So
should be fine.
yeah. So it means like it's like learning by doing. I mean, so everybody gather together and then give some idea and then work
Yeah,
together with the program and help with each other, something like that.
right, exactly.
Okay. Yeah. Well, it's a good experience, especially for our students, so they don't need to be worried if they want to learn about computational modeling in nuclear reactor. Thank you very much, Sensei, for your explanations.
Thank
Bye.
you.
Terima kasih, thank you Pak Panji atas pertanyaannya juga jawabannya dari Yamaji Sensei. No, I think time is already near finish. So I will conclude Yamaji Sensei presentation. It's easy because Yamaji Sensei already stated in his summary. I just read from your presentation. Summary of this presentation that developing and designing reactor system is required the multi-level physics modeling. So bagi mahasiswa fisika tentu ini hal yang baik ya untuk Then the conceptual course design requires beberapa hal such as reactor physics, reactor thermal hydraulics, also fuel for performance modeling. Then the last that recent advance in computation power and tool are enabling application of advanced simulation methods for safer accident analysis. Then finally, as a moderator, I will thanks to Yamaji Sensei for your presentation. It's very interesting. Ontoni arigatou gozaimasu. Also, I would like to thank all your kind attention. Arigatou gozaimasu. And time is to Master Ceremony, Master Fajar. MC, time is yours. Arigatou gozaimasu. Terima kasih.
Thank you very much. Arigato gozaimasu, Yamaji Sensei, and Mr. Dr. Eko Hidayanto for the moderator. Thank you very much, Yamaji Sensei, for informative and insightful presentation. This time, I would like to call Yamaji Sensei to receive the certificate from our department. Kindly please, the head of Department of Physics, Mr. Professor Dr. Heristanto, to pass the certificate to our honorable outstanding speaker, Yamaji Sensei.
Yeah, thank you, Mr. Fajar. Thanks. Professor Yamaji, thank you very much for your attendance and participation as speaker in our webinar on physics. On behalf of the Faculty of Science and Mathematics, Diponegoro University and Physics Department, we want to express our great appreciation and gratitude for your presentation by awarding the visiting professor certificate. We hope to maintain the relationship between Diponegoro University and Waseda University and welcome for further collaboration
Tanya,
with the physics department Diponegoro University. Thank you very much. Arigatou gozaimasu.
Thank you very much, Professor Heristanto. Thank you very much, Yamaji Sensei. And then we thank you for Mr. Dr. Engineering Eko Hidayanto. And we have the certificate for Dr. Eko.
jam.
This is our certificate of appreciation for Dr. Eko Hidayanto as the moderator.
Okay, thank you, Mr. Fajar.
Thank you. Ladies and gentlemen, finally, from the deepest of my heart, I do apologize for my mistakes in the presenting this event. Thank you very much for your attention. And then the photo session, Yamaji Sensei. And ladies and gentlemen, activate the camera, please, because we would like to take photo.
Capture Mas Faisal fotonya.
Mas Faisal?
Iya, Pak.
Silakan di
foto
fotonya.
Please, ladies and gentlemen, activate for your camera because we will to take the photo session. Sudah, Mas Faisal?
Sudah, Pak.
Okay. Thank you very much, and thank you very much for the ladies and gentlemen, and especially for the Yamaji Sensei from Waseda University. I hope someday I can join in your laboratory. Maybe, inshallah.
Yes, thank you. So I have had
Wingi kita ya, Bang.
Okay, thank you very much, and
I will try to visit you.
Ilham kok ngerti ano snack kan lo.
Thank you. Arigatou gozaimasu, Yamaji Sensei. I think it's enough, ladies and gentlemen, and finally, from the depths for my heart, I do apologize for my mistake in the presenting this event. Thank you very much for your kind attention. See you later. Goodbye. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Yamaji Sensei. Arigatou gozaimasu. Terima kasih Bapak Ibu serta hadirin yang sudah hadir pada acara hari ini. Mohon maaf banyak kurangan. Saya Fajar Arianto dan tim. Mohon maaf apabila dalam menyampaikan acara pada sore hari ini. Selamat berjuang.
Ini juga ya, mengisi presensi kehadiran untuk dikirimkan sertifikatnya. Mungkin barangkali ada yang lupa belum mengisi. Ya, gitu.
Ya, terima kasih Bapak Ibu. Sudah, saya ulangi. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh.
Terima kasih Pak Zainul, Bapak Ibu yang sudah hadir. Ini rekaman sudah selesai nih Pak?
Ya, sudah selesai Pak Fajar.
Baik, Prof. Heri. Terima kasih Prof. Heri atas
sama-sama
kesempatan yang diberikan.
Baik, kita tutup ya, materi izin lip. Ya, Assalamualaikum.
Salam.
Waalaikumsalam.
Ya, Assalamualaikum.
Salam.
Waalaikumsalam.
Iya.